What's up, 7th grade? Mr. Pastel here. Today I want to do a better job explaining carbon dating or radiocarbon dating better than I did yesterday because I don't think I explained it very well, the principles behind it. So let's say I find a fossil in the ground, such as this one, something that I think is a fossil. How can I tell how old it is? Um, well, let's start at how carbon decay actually works. So, we know that during photosynthesis, plants absorb carbon dioxide from the atmosphere. Um, when it comes from the atmosphere, there's actually a form of carbon called carbon 14 because of the ultraviolet light of the sun. There's a specific form of carbon called carbon 14. Um, this is not normal carbon that we have in most of the earth. That's carbon 12. Um, so during the beginning of this whole process, you start with carbon 14, and when a creature such as a turkey, let's say, eats the plant, it absorbs the carbon 14. Eventually, that organism is going to die, and once it dies, the carbon starts to decay into something else. And every 5,730 years, the amount of carbon 14 is roughly cut in half. So, once you find the fossil, you can see how much carbon 14 is in it. And basically, the less carbon 14 that you have, the older the fossil. So that was an example of a turkey, but let's go to a different example. Um, well, basically, what you can do is once you send it into the lab, you take a very, very tiny piece of the fossil using you take a little sample here. Let's go to the example of the saber tooth. Okay, here we go. So, if a saber tooth tiger dies, um, when it dies, it still has 100% of its carbon 14 that it had when it was living. But then, because it's not living anymore, that carbon 14 starts to decay. So, after 5,730 years, you have 50% of its original carbon 14. After two half lives, 11,460 years, you have 25% of its carbon. After 17,000 years, you have 12.5% of its carbon. So as time goes on, you get less and less carbon 14, and eventually you have nothing. No carbon 14 remaining. Now, saber-toothed tigers are fairly recent in terms of the eras of Earth. So, saber-toothed tigers, you can use carbon dating because I believe saber-toothed tigers and early humans were around at the same time. But you can't use carbon dating for dinosaurs because now we're talking millions of years. So you have to use an isotope different from carbon. Woolly mammoths, same thing. They were also around during the time of saber-toothed tigers. So you can actually make a graph of the amount of carbon 14 after the mammoth dies. So after 0 years, you have 100%. After one half life, you have 50%. Two half lives, 25%. Three half lives, 12.5%. Four half lives, 6.3%. 3.1%. And then it just keeps going down. So carbon dating is used for basically human era fossils, but you can use a different kind of radioactive dating for dinosaurs. So let's get down to your actual assignment. I put my data into this Google Sheet, which is basically like Microsoft Excel. So I put my trial 1 here, and I put my trial 2 here, and then I generated a graph for each one. Now, what I want you to do is to replace my data for the remaining carbons with your data. For the first trial, actually leave that 20 there, assuming you started with 20. So replace these numbers that I'm highlighting, and then replace these numbers that I'm highlighting for your second trial. These graphs should automatically update. So you can see, if you start with 20 carbons, how quickly they go down to 0. So for my first trial, it took 7 half-lives to go down to 0. But yours is probably different. It may be 6, maybe 8, maybe 5, maybe 9. For my second trial, it took 8 half-lives to get down to 0. And yours may be different. So once you have the graphs, let's do the analysis. How many half-lives did it take in the first trial? For me, it was 7. How many half-lives did it take in the second trial? For me, it was 8. If the half-life of carbon is 5,730 years, multiply that by the number of half-lives in the first trial. So I would do 7 times 5,730. And then for my second trial, I would do 8 times 5,730. That's the time that it takes to completely decay, all the way down to 0. Why was there a difference between the first trial and the second trial? Well, there's always variation. So if you actually look at individual carbon atoms, you can't tell. You can't predict which one will decay and which one will not decay. But if you have, even in just a tiny, tiny sliver of a sample, you probably have trillions of particles. So in that case, it's going to be a nice clean number, like 50%, 25%. Last question. How do you think scientists use radiocarbon dating to estimate the age of rocks and fossils? This is the most important question. So if you can just summarize what I said earlier in the video. But basically, you take a sample of your fossil or rock, and you see how much carbon-14 isotope is in it. So the older the fossil, the less percent of carbon-14 will be in it. So you're looking at, like, where is it in the curve? Is it near the beginning of the curve? Is it near the end of that graph curve? Does it have 50% of its carbon? Does it have 2.7% of its carbon? So basically, the less percent of the carbon-14 that it has, the older the fossil. So I hope that's helpful. Let me know if you guys have any questions about carbon dating.